Hi everybody and welcome back. So yeah, I guess this McIntosh MC2100 just keeps coming up. And that's great. That's great. I mean, that's why I do this channel. You know, we get discussion going and we exchange information with one another and share our experiences with this equipment with one another. So this is all really good stuff, so I'm happy. So I've been getting quite a few emails. I see that there's a few forums out there that have mentioned this project a little bit. So I thought I would just take a short video and kind of clear the air with some of the things that I'm hearing out there. First of all, I really did not, nor do I have any intention to produce these boards and sell them or market them. When I did this project, I had a couple boards left over. I mentioned in the video that if somebody was interested in them, that I'd be happy to work something out with them, and I got an overwhelming response of people who wanted these boards. So I placed a second order for an updated version of the board that I made, so that you can actually mount the little mounting stud in the same place that the original boards had. And I basically sold those really not at much of a profit or anything, but just at a cost to get them out for some experimenters. It's written right on the board for experimental purposes only, and that's really all it was. And from what I've heard back from the people who did get those boards at that time, and I'm pretty much out of them now, I don't have any more. I have a few that I'm going to keep for myself on the side, but that's it. Was that the boards did work and they're performing very well. So that was all good news. Now, of course, no matter how many things you do, there's always, if something has a lot of interest in it, there's always going to be more information that people are going to want to know about something. So I thought, well, I'll go ahead and try to address some of those questions to the best of my ability anyway. I am not a McIntosh expert, I'll be the first to admit it. I love McIntosh equipment, but I'm not an expert at it. So when I built these boards, it was out of a necessity. It was because when I purchased this amp online, I got it very inexpensively, and it did not have the boards they were missing. So I had two choices. I could buy the board pre-made from McIntosh, and to my understanding, they're still selling them. They have great customer support. Or I can make a project out of it and build this board. And really, my goal wasn't really to try to reproduce what McIntosh already did or anything like that. And honestly, if I wanted one of these original boards and was worried about originality, I would buy one of these in better condition with the correct original boards, and that would be that. So really, that was never the intent on this project. It was to see if we could reproduce a board that could use modern parts that we could order from the modern parts houses such as DigiKey or Mauser or somebody, and if it would perform at least similarly to the original boards. From my testing, that's what it seems to be doing. These seem to work pretty well as a substitute. Now, I don't have one of these in front of me with the original boards in mint condition that I could put the two side by side and do a comparison. That's really the reason that I printed up a few more of these boards and let them go out to some of the viewers who had the wherewithal to be able to build these boards their own way and test them out. And the results I got back was that yes, these work pretty well compared to the originals. So that in mind, I heard, you know, well, you didn't do enough testing, and we want to, you know, these amps are really have a reputation for being very, very durable and indestructible and bulletproof and all this, and we really would like to see it tested in that manner so that we could see if this performs the same way as the original. And I thought, what a good idea, let's try that. I mean, I have nothing to lose on this, guys. I picked this up very inexpensively. This was just a project. It's probably not worth what a mint condition one would be. It's got rust on it and things, and I didn't really go crazy with the restoration, but really kind of left this as a rat rod, you know what I mean? Some of you car enthusiasts out there will know what that term is. So anyway, let's test this out, and before we do that, let me address a couple of questions that I had about the design of the circuit. One of the things I regret that I didn't do enough was kind of explaining some of these circuits and what they were, or even in some cases not clarifying some of the things I said. So we're going to try to correct that. So let's do that first, and then we'll throw this up on the test equipment and just see how it works. So the first thing I want to go over on the schematic is a little more clarification on what this little circuit right here does. The formal name that McIntosh gave to this is the Sentry monitor circuit. I believe that's what they're calling it. And really, what its main purpose is to prevent overcurrent in the output section. In other words, if you have a difficult load on here and it presents a high current situation, let's say the speaker shorts out and you short your speaker terminals or something like that. Let's say this transformer here shorts out. What's going to happen if we overload this? Remember, you only have these 2 transistors to carry all that 100 watts of power, and you have these current limiting resistors, and of course normally in a conventional amplifier that doesn't have any overcurrent protect circuit, these will just open up and go away, and that opens this whole line here to prevent shorts from happening and any further damage. But of course, usually by the time this happens, you've already damaged your transistors. So when I referred to this circuit, I kind of tongue-in-cheek referred to it as an anti-clipping clipping circuit. I think that's what the term I'd use. I'd have to go back and look at the video, and I very rarely watch my videos after I post them, but that's what I meant by that. And so if you look at these, the purpose of these is, and I went over some of this, these little Darlington transistors, first of all, this concept is nothing new. If you just go back one video to the Marantz that I worked on, the Model 15, it had a similar circuit that performed a similar task in a little bit different manner, but it's the same idea. And even if you went back another video like to the Kenwood and some other things, some of them will have this same circuit, but instead of having a monolithic Darlington transistor like this, they use 2 discrete transistors in a Darlington configuration to get the higher gain. But really the whole purpose of this is, you see these resistors here. You have, for instance, here you have on this side, you have R27, you have R23, and you have R19. And what these are going to do is, you notice they're tied right in directly over here to your outputs. So here's your outputs. It's monitoring the voltage coming off of here. Now remember, you're looking at the voltage drop with reference to this center point across this resistor. So really, by knowing the voltage here, we can calculate the amount of current here in this resistor. And when we know what the current is here, that voltage will represent that, and we know what the maximum current is that the circuit can handle through the design. And the whole idea is, when this voltage climbs above a certain level, this voltage divider here will put a signal onto the base of this Darlington transistor, and eventually there will be enough signal here to turn this on, or begin to turn it on. Once this turns on, it's going to take the signal from your little preamp circuit in your driver circuit here, this whole driver circuit coming from your preamp stage, and it's going to shunt it right down to your common point here. So essentially this is sometimes referred to as a fold-over circuit, because what this is doing is it's monitoring the output and then folding it over to here and closing out this signal going in from here. So it is clipping the signal and it's not clipping it by overdriving it, it's clipping it by reducing the maximum level that this thing can reach. In other words, this acts like a variable Zener diode, I guess you could call it. So whenever you exceed the voltage that is set up by biasing this base, then it's going to crop that off. So it's not going to allow the drive that you need to overdrive this into an overcurrent situation. So it's just a loop. And that's how these work. And there's one for the positive going half cycle, and there's one down here for the negative half going cycle. Now that being said, you can take these transistors totally out of the circuit and the amplifier will play just fine. You won't notice any difference in sound quality or anything. But what you will notice is if you drive the amp into what I call hard clipping. In other words, you drive this all the way to the maximum rail voltage, and that rail voltage comes through here and goes through a very, very low impedance, a low resistance, and creates a very high current situation because of Ohm's law, right? You're going to overload this transistor and this resistor, and you're going to cause something to eventually burn out. You'll either short the transistor or it'll open, or you'll blow this, hopefully blow the resistor open first. But we don't want that to ever happen. So if you overdrive the amplifier, all it's going to do is it's going to what we call soft clip. Soft clip means it clips the signal, but it doesn't clip the actual output section to the rails. And that's what its whole idea is. So that's kind of why I jokingly called it an anti-clipping clipping circuit. It prevents the output stage from hard rail clipping by clipping the input to it first. So that signal never gets high enough in amplitude to allow this to overdrive into an overcurrent situation to your speaker load. Does that make sense? I hope that does. And again, there are two different circuits that McIntosh used. This amplifier only uses the first one, called the Sentry monitor circuit. That's what they call this. Pioneer and some of the other companies just call it overcurrent protection circuit. And it's always a similar situation where you're looking at the output, you're feeding it through a voltage divider, that goes into a high gain transistor fold-over circuit that will squelch out the input to prevent overdriving this into an overcurrent situation. And that's what they do. Now the other circuit that does not exist on an MC2100, they refer to as power guard. And power guard, and you can read about this, they really prominently talk about this, McIntosh does, in their brochures. So the power guard is something different. It actually works at the front end of the amplifier, and its whole purpose is when it sees an overdrive situation, it reduces the gain of the front end of the amp so that you can't drive the amp into distortion. Because think about it, you're still going to get distortion with this. All this is going to do is protect the amp from damaging itself by having an overcurrent situation. You're still clipping the signal, and so that clipping is going to be actual distortion. It will cause distortion. And I had several comments saying that this is the purpose of this is to prevent distortion. It is not. The amp will still distort, because anytime you remove part of the waveform of the original signal, you're causing distortion. In other words, you're now changing the signal that was coming in here to a different signal, to a clipped off signal in this case. And that's what this is doing. So yes, it'll sound distorted, but no, it will not allow an overcurrent situation to damage the speakers and the transistors out here. Power guard is different. Power guard will reduce the amplitude of this signal to prevent it from clipping. So it will never let the amp drive at such a high volume that you will get a distorted signal by pushing too strong of a signal in. So if you have too high of an amplitude of drive signal, this will compensate by lowering its gain so that this still stays undistorted clear up to its maximum rated power. Again, that does not exist in an MC2100. The power guard circuit is in the later models of McIntosh equipment. So I just wanted to clear that up so the non-McIntosh people or people new to this circuit or to this type of equipment, so they understand how it works. So that's how that works. Now, last but not least, I just want to talk about this real quick. This is another confusing situation. This amp does not really have a DC offset adjust, nor does it need one. Well, why would you say that I don't need an offset? Because remember, the only matched transistors are here, and even that, when you look at this circuit, it is possible for these to not be perfect. But it doesn't matter. And the reason it doesn't matter, at least to a small degree it doesn't matter, if there were any kind of DC offset, this, if you notice, as a DC signal anyway, not as AC, this is a very thick, short, low resistance piece of wire. So for all intents and purposes in the DC world, not AC, but in the DC world, this is shorted to ground all the time. Through this transformer. That's the beauty of this transformer. And with that being said, even if something shorted up here, for instance, this transistor, let's say it does short. Let's say the Sentry monitor does not do its job. This transistor fails. It goes dead short. And this resistor takes the heat, but it doesn't blow open. All that current would go through your speaker normally. But in this case, it does not. It goes this way, it goes around here, and straight to ground. And your speaker, regardless of its 4, 8, or 16 ohms, that speaker is actually going to be in parallel with this. And this coil from here to here, along with the speaker voice coil from here to here, is a higher resistance than this little piece of the coil right here to here. So actually, you're going to have a voltage divider with most of the voltage and most of the current, I should say, going through this. You're going to have a current divider. I'm sorry, it's a parallel circuit. These two it's a current divider. The higher amount of current will go through here. So even though the speakers would take a little bit of a hit shortly, it would be much lower because of this, and then you would blow this resistor open. So it's a very safe circuit on speakers. It's very difficult to blow a set of speakers with this amplifier unless the speakers physically aren't designed for a 100-watt RMS amplifier. Last but not least, because of this transformer, your impedance load is the opposite of what it would be in a non-transformer transistor amplifier. And what do I mean by that? Well, let's think this through for a second. If we just eliminate this whole part up here, so we just ignore this top part of the coil. So now all we got is this, okay? See that? So you have output of the amplifier, comes through here, goes into here, and to ground, okay? So as this thing operates, now we're talking AC instead of DC, this just acts like an inductor. And that inductor absorbs the energy, right? And it will draw, depending on the inductance, it will present a certain amount of current load, RMS, to this output section. Now, if you put a speaker on here, let's just say, and let me grab a pen. So let's just say we put a speaker, we're going to do an 8 ohm speaker, for instance. So here's my poorly drawn speaker, right? So there's a speaker. What is happening now This is called an auto transformer. So what's going to happen is you still have plus and minus 35 volts. That can never change. And without the transformer, the speaker determines the maximum current that you can get through this and the maximum wattage. In other words, if I put 35 volts across an 8 ohm load, and I put 35 volts across a 4 ohm load, and I put 35 volts across a 16 ohm load, I'll get 3 different wattages because of Ohm's law. And with this, it's the opposite. You have an auto transformer. So the voltage here is always a 2 ohm load. Or the impedance, I'm sorry, the impedance right here is always a 2 ohm load with respect to this plus and minus 35 volts. And all that's going to happen is this multiplies the voltage. And so if you have a 4 ohm load, you're still going to have plus and minus 35 volt rail to the speaker. And you're going to have a higher voltage, and this has to deliver higher current because of the amount of current that that voltage will cause on that 4 ohm load. If you have an 8 ohm speaker connected up here, the transformer will step the voltage up even higher because this is a transformer. And the current as a result of that voltage will be based upon the 8 ohm load. The current in this 2 ohm section will be even higher yet. So the higher the impedance of the speaker, the higher the current draw is going to be on this circuit. Whereas in a conventional amplifier without the transformer, if I just connected my speaker directly to here, the higher the impedance, the less influence that voltage will have on that impedance, and the lower the amount of current that will be drawn. And if you take current times voltage, you'll find that your wattage goes down as your impedance goes up. That's why if you look at a normal stereo, it'll say, you know, 50 watts per channel into 8 ohms, and it'll say maybe 70 or 80 watts into 4 ohms, and it'll say 25 or 30 watts into 16 ohms. The reason that it's different wattage for different ohms is because you only have this voltage that you can apply. It never changes, right? This is the maximum voltage. It never goes above this. So as you change the resistance, or quote unquote impedance, the current will change as well because of Ohm's law, right? I, E, and R. So I equals the voltage divided by the resistance, or the voltage divided by the impedance in this case. And you can see very quickly that your current goes down as your impedance goes up. Whereas with this transformer, that takes that out of the equation. So it's the total opposite. As you drive this thing harder, or with higher impedance load, this has to draw more current at 2 ohms to give you the same amount of wattage at 16 ohms. So I hope that kind of makes sense. So this actually will increase in wattage to make sure that you can get that full 100 watts at 16 ohms. That's why no matter what speaker you have, you get a full 100 watts out of this amp. And on the ones that don't have this transformer, that is not the case. Make sense? Probably not. Clear as mud, I bet. So, I don't know. Hopefully that's my my attempt at explaining how this works. But I hope that clears that up. And that's one of the reasons these things have such a unique sound to them, because they're not affected by impedance quite as much as the amps that don't have this transformer, because you can always pick a tap that will as closely match the center impedance of that speaker load, you know, as you can, whereas other amps don't have that. Hope that helps that a little bit. So now let's dispense with the schematic and let's do a few tests on our amp according to what some of you asked for. Okay, for starters, let's give you the setup. We're going to try to demonstrate what we were just talking about with the autoformer and how it reacts to keep the wattage the same regardless of what kind of speaker you connect. So if you look here, we're hooked between common and 8 ohms on both channels, and on the left channel I have these extra leads that are going over to a voltmeter. I'll show you that in a second. And you can see on the dummy load we're switched down to 8 ohms on each channel. So we're putting an 8 ohm load onto the amplifier. Now, if we look here, what I'm going to try to do is get this all in shot. And I want you to look at a couple things here. We're going to drive the amp until we get it into clipping on both channels. We are then going to look at the wattage, how many watts the amp is putting out, and that's going to be this red display right here. And we're going to look at how many volts RMS is on that channel to produce that amount of wattage. Okay, does that make sense? And we're at 8 ohms right now, so that's what we're going to look at. So let me get the amp set up, and then we're going to look at that. All right, now I have the amp set, just the signal generator to drive the amp just to clipping, which is going to be a little bit over 100 watts. And I want you to look at the wattage here, look at the waveform, and then look at how many volts RMS it takes to give us that. Here we go. And you can kind of hear those transformers singing. You see that? We have about 29.4 volts RMS to give us about 108 watts RMS. And watts RMS, that doesn't really count. 108 watts. Okay, so that's done. So we see that. Now what we're going to do is we're going to go over here to the dummy load. And the first thing we're going to do is we're going to shut the amplifier off. We're going to change this to a 4 ohm load. And we're going to go down here and we're going to move the wires from the 8 ohm tap to the 4 ohm tap. That's all we're going to do. And then we're going to do that same test over again. Okay, I've changed the program on the scope to accurately measure wattage at 4 ohms. We've changed over to our 4 ohm load and we've moved our taps over and we've moved our meter over to that 4 ohm tap. Let's turn it on and let's look at the watts. Again, 108 watts, but look at our voltage. It is lower. So what it is doing is it's adjusting the voltage to give us the correct wattage at that selected impedance. Now watch what happens if I switch an 8 ohm load onto those 4 ohm taps. So we're on 4 ohms now. Let's go to 8 ohms and watch what happens. Same voltage, right? Still about 21 volts. But if you look at our wattage, make sure that it's set correctly. Wait till it measures. And you can see our wattage is now 54.7 watts. So if we just used that 4 ohm tap for every type of speaker impedance, with the same voltage out, you get a different wattage to your speaker. In other words, you're driving the speaker with less power. Does that make sense? So that's the whole purpose of that autoformer. And again, this is nothing new. This is the way it was done with vacuum tube amplifiers for many, many years. But when we went to solid state amplifiers, they work on low impedances very well, and they did away with the impedance matching. You just had your rail voltages, and the maximum rail voltage is what you got, no matter what. And so it works, but not as well as it could. It's not as efficient. Now, again, the trade-off on this is when you use that autoformer, the higher the voltage you're driving into the higher impedance speakers to get the same wattage, the more current you have to sacrifice from your transistors to produce that extra voltage. So it's a trade-off. Anytime you lose something, you have to gain, or gain something, you have to lose something somewhere else. So to gain that, you know, to get the higher voltage, you gotta get a higher current, right? So there's always a trade-off. One thing costs another thing. So there you have it. And by the way, all this time that this has been running, I know a lot of people were asking about, you know, how this amp works under, you know, under load. Well, it works extremely well. So what we're going to do is, let me put this back into, since we're hooked up to a 4 ohm load, let me go back to the 4 ohm reading, and let me change the speakers. And you can see nothing changed as far as your voltage right there, because we're using the same tap. We didn't move the tap. But what happened to our wattage when we went from an 8 ohm to a 4 ohm load? Big time. And you can hear the transformer whining from all that power. And this thing's just sitting here chugging along at 108 watts. Remember, this is a 100 watt per channel amplifier. It's got a lot of headroom though, because of its design. And this thing can sit here and do this all day. It won't matter. It won't hurt it, not even one bit. It doesn't care. So here we are, chugging along. And these are, I mean, barely getting lukewarm. Remember, you're only dissipating 100 watts of energy, and you've got these two great big heat sinks. So you're not really going to get a whole lot of, you know, it's not going to get super duper hot. So there you go. That's the one test. And I hope that explains how an autoformer works and why it's a good idea. What's the downside? Well, she's a whiz, this thing's huge, weighs a ton. These are extremely expensive. They're not a normal transformer. They're a special tri-filar wound auto transformer. And so the cost and the weight and the size of the amplifier goes up a lot when you use this technology. In addition to that, you have to have an output section capable of delivering a lot more current than an amplifier that does not have those autoformers on them. Because it's really it's self-regulating when you don't have these transformers. In other words, the higher the impedance you put on, it just draws less current. So the worst that can happen is if you put a real low impedance load on it, and that's the only time these will draw heavy current, when you don't have an autoformer. But these guys draw heavy current all the time when you have an autoformer, regardless of what impedance you connect. So I hope that makes sense. But I'll keep it cooking while we're talking here, and we'll just see what happens. You know, 108 watts per channel right now, just all day long, this thing will do it, and it'll never warm up. All right, I hope I can keep this in frame and in focus and all that stuff, but there's your heat sinks, and there is your temperature. The transistors themselves are about, the cases are about 30 degrees C, and the heat sinks are about 43 degrees C, and all of them are very similar. And this has been running now for about 10 minutes or so since we just went from the last clip. And if you look, it's been so long that actually the meter went to sleep, and we're still, I'll zoom you in, we're still looking at 108 watts per channel, and it's still rock solid. And like I said, I can leave this all day. It doesn't care. It'll just keep doing this. And they're all a little bit pretty much the same. This side of each channel is a little bit warmer than this side. And it's both channels are like that. Part of that is because the current limiting circuit in my boards is a little bit out of balance. And what do I mean by that? Well, what I mean by that is that these voltage dividers here that I have in there are still not perfect. Remember, we kind of used a different type of Darlington transistor. So depending on what Darlington transistors you have in here, if they're different than the original ones from McIntosh, you may have to play with these resistors a wee little bit to get it to totally symmetrically fold over. And I'm noticing that the fold over circuit is a little bit asymmetrical. So you'll see that one side will clip a little bit soon. In other words, it's the fold over circuit is not clipping at the right time. It's not shutting down the drive signal at the right time. So if I go up, you can see how the bottom is clipping a little bit before the top hits, and then the top goes. See, they're just a little bit off. We can balance that if we go ahead and play with those resistors. That's the purpose of that voltage divider in there. Again, I just never messed with it that much. I could play with this amp forever, you know, but you get so many projects on the bench that you got to get done. But one day I will do that. We will mess around with those resistors and we will get it perfect. But you can see it's still, turn this back on and back out a little bit. Still rock solid 20.6 volts RMS into 4 ohms. And my dummy load speakers or resistors are, they're getting warm. So that's another thing. I'm driving the crap out of my resistors, but they're 1,000-watt dummy loads, so really it's not a huge deal for them. They can take that. I can run it all day. You can see the size of those massive aluminum resistors underneath the circuit board there. So anyhow, and yes, I'm just kind of chattering on here because I just kind of want to show you that it's right now it's at the temperature it's going to be. It's not going to get any warmer than it is. I mean, it's not. It is what it is. So there you go. That's the durability of the McIntosh amplifiers. They're tough, and that's why you saw these used even in commercial, you know, like in concert venues and so forth, because you just can't kill these amps when they're working correctly. They're really well built. They're overbuilt, if anything. Oh, and yes, I know people are going to ask, are you driving both channels? Well, yeah, actually I am. There's the other channel, and you can see they're just tracking so perfectly you can't even tell. When you line these up on top of one another, it doesn't matter which channel, you know. They're right and left are identical. So isn't that amazing for an amp that has just a cheap potentiometer for the trimmer in the front end and so forth? Pretty cool. Okay, I think we've already done this in the previous tests, but I'm going to do it over again. 1 kilohertz tone, driving it just before clipping at 108 watts and looking at the THD. And you can see we're getting about 0.03% THD at 100, well, it's 98 watts. We can go up a little bit, I guess. See here where we're at. Let it measure. 102, right there. 107 watts right there. 111, I'm sorry, I'm running a little bit hot. And you can see it's climbed up now. Take it just closer to that 100-watt range where it's rated. Come on, read. There it goes. 107.5, and you can see it's pretty low. So the amp's doing its thing. Works very well. And it kind of jumps around a little bit, but, and you can see that's the influence of the bias circuit kind of going up and down and changing. It's trying to hold that, and it's doing a very good job of it. So that's just a quick test there, and let's do another test. Okay, we're driving the amp with a SMPTE pattern for intermodulation distortion, which is the 60 Hertz with the 7 kilohertz tone at a 4:1 ratio. And the amp's grunting and groaning under the strain. And looking at the 7 kilohertz, hold on, I just moved it. You can see right there, the side bands are what actually determines the amount of intermodulation distortion. And you can see they're wee little there. If there was high IMD, you would see these little side bands on either side would get bigger in amplitude, and they would kind of curve down this way. You wouldn't have that real sharp transition from noise floor to the signal. So what that means is the IM distortion is very low on this. Now not calculating the percentage, we're just visually looking at it. So let me shut the signal off. And I'll show you, well, before I do that, I'll show you what the signal looks like. There's what it looks like. So you see the 60 Hertz, and you can see the 7 kilohertz is that zigzaggy part riding on the 60 kilohertz, or 60 Hertz. And you can see the 60 Hertz is 4 times the amplitude of the 7 kilohertz. So that's what you're looking at. And of course the scope's kind of triggering funny because I didn't mess with the trigger a whole lot. So it's kind of false triggering a little bit because of the 2 frequencies. But there you go. So this amp all the way around, it performs very well. Other than I need to adjust those resistors, I could fine tune that a little bit for the Sentry monitor. The difference is though, you're not going to probably see that at full power, but it just means that it may allow excessive current on one side versus the other when you exceed maximum power. So it should be addressed, which I will probably do someday. All right, on our next test, we just did our square wave, and we're doing it just about at peak power, but not quite. And what you can see is we have just about 1 division here from just slightly above where it starts climbing till slightly below where it starts leveling off. And you can see we're right around 4 microseconds, a little bit over 4 microseconds, and that's going to come out to somewhere around 12 volts per microsecond, which is right on the border of being pretty decent. And again, that would be one of the limitations of these transformers. Now, if you put a normal auto transformer in there, you probably would never see anything like this with an iron core transformer. This is because of the special trifilar wound autoformer that McIntosh uses, that you're getting pretty respectable rise time on this and slew rate. So if we go, let's see here, trigger. If we go on the falling edge, let's see if we can capture that. And I want to go falling edge. And once again, very similar on the falling edge, same kind of thing. And notice, it is absolutely as pure and clean as it can possibly be. There is no ringing, there's no ripple, there's no oscillation whatsoever. So again, this is a very stable amplifier. I know another question was, will the amp oscillate? Because there's rumors that these amps can actually have some parasitic oscillation, especially if you use the wrong transistors. Well, with the setup we have here, it looks to be pretty solid. And if we drop our time to get the whole square wave into the signal, let's see, shrink this down. I don't want to leave this on forever. You can see it's pretty nice. That's about as square of a square wave as you can get. And again, you're going to have a little bit of slew rate. And remember, part of this is also the test equipment. You know, you have cables, you have the dummy load itself, you have the autoformer. There's a lot of things that can add to your slew rate. So considering all things considered there, very nice looking square wave on this amp. Remember how old this technology is and when they built these things. Not too shabby. So that being said, this video's already gotten longer than I really wanted it to be. I didn't want it to be a super long video. Funny, short videos and Tony. Not a very, that doesn't happen too often, does it? But anyway, that's it. That's what I'm going to wrap this one up right here. I hope this answered some of the questions that were floating around out there. And if you have any other questions or comments, feel free to post them, and we'll be happy. I know if I can't answer them accurately, there are a lot of smart people that watch these videos, and probably a lot smarter than I am, and I'm sure they'd be willing to share their answers with you as well. So again, thank you all for your all of your good comments and so forth, for your emails and donations and all that thing, and I appreciate it. And even though I'm very busy and I don't always have time to totally respond to everybody all the time, just know that I do try to read as many, if not all, of the comments and emails that I get, and I try to answer as best and as much as I can. And I appreciate all of you, and thank you. I wish you all peace, joy, happiness, and good health in your lives as always. And until next time, stay well. We got some more things coming here onto the bench very soon, so we'll see you soon. Bye-bye.